Hello friends, this is the third session on numerical analysis of BSc 5th semester. In this video, I would like to explain you two more examples on errors, absolute errors, and relative errors and percentage errors. So let us consider the recap of the previous things, what we have done in the previous session. We have defined the concept of error, and we have seen three different types of errors, namely absolute error, relative error, and the percentage error. So this we have seen in the previous video. Now in the present session, we will be able to understand the method of solving a couple of different types of examples on absolute error, relative error, and percentage error. And now let us solve another example on errors. So here is the next example given to us. Here we have to find the absolute error, relative error, and the percentage error of the number x, which is given as 3.7. X is 3 by 7, which is approximated as 0.428. That is, if 0.428 is approximate value of 3 by 8, find the absolute error, relative error, and percentage error. This is the question. As usual, we have to consider this as x, and 0.428 is given as its approximation, that is the approximation of x, that is always denoted as x dash. Now the definition of absolute error is very simple, that is EA equal to absolute of numerical difference between x and x dash, that is x minus x dash. X value is here, and this is the value of x dash, absolute value. And now we have to simplify this. We can use the scientific calculator and we can simplify this, and then we will be getting the answer as 4 by 3000. So this is the absolute error associated with the number 3 by 7 when it is approximated as 0.428. Now let us simplify this 4 by 3000. If we simplify 4 by 3000, the answer is going to be 0.0005714,286. This is the simplified form of this, and this can be taken as the absolute error in the further computations. So let us go for the evaluation of relative error. The relative error is defined as absolute error divided by the absolute value of x. Absolute error, in the previous section we have seen that absolute error is computed as this much, and the value of x is given as 3 by 7. Now if we simplify this, the final answer will be this much, and the relative error is 0.001333334. So this is the relative error in the given number x. Finally, the percentage error, very simple formula we are having, that is relative error multiplied by 100. So if we do that, relative error we have computed in the previous step, here it is there, so the same value we will be taking here, and if it is multiplied with 100, the answer is 0.1333334. So this is the required percentage error. So in this way we have computed the absolute error, relative error, and the percentage error in the evaluation of the number x when it is approximated as x is 3 by 7 here, when it is approximated as 0.428. We have seen what are the different possible errors. That is the absolute error, we have seen it as 0.0005714,286, relative error 0.001333334, and finally the percentage error 0.1333334. So this completes the solution of the first problem. Now In the second problem, if you look at this problem is quite different than the previous one. Here the question is to find the absolute error. Again we have to find the absolute error in the number. The given number is this thing. If the question, you please see the question, if it contains 5 valid significant digits, 5 valid digits. So this is very important at this moment to know what is meant by the valid significant digit. So in order to have a look at a valid significant digit, I would like to explain something to you at this moment. That is, we know that any given number, this is the new concept I'm going to define you, that is valid significant digit. We are defining over here, and this particular thing, let us see here. If you have a number, for example 2354, right from our primary school we know that how to write this number in an expanded form. It is 2 into 1000 plus 3 into 100 plus 5 into 10 plus 4, that is the unit place. This is the unit place, 10 place, hundreds place, thousands place. So the expanded form looks like this. And this is the fractional number. If we have a decimal place, how to write this is? We know that this is ones place and this is tens place. This is 1/10 place and this is 100s place. That is the decimal places we know. And how to write in this case? This is also in the same way, 2 into 10 plus 1 into 10 to the power of 0, that is units place, plus this is 3, but it is in the decimal place. So it is 3 into 10 to the power of minus 1, because it is 0.3 means 3 by 10. So it is 3 by 10 to the 3 by 10 means 3 into 10 to the power of minus 1. This is 0.05. That is nothing but 5 divided by 100. 5 divided by 100 is nothing but 5 into 10 to the power of minus 2. So this thing we very well know from our primary school. If we know this concept, then we can very easily define what is meant by valid significant digit. In general, any number, if x is a given number which is having these many digits, alpha 1 is the first digit in that, alpha 2, alpha 3, alpha 4, dot dot dot, alpha n dot dot dot. These many digits are there in x. It can be expressed in the same way how I have shown you over here. In the same way, the value, the number x can be expanded like this. So here alpha 1, alpha 2, they are the digits which are constituting the given number. For example, 2, 3, 5, 4 were the digits constituting the number 2354. Like that, here alpha 1, alpha 2, alpha 3, dot dot dot, they are the digits which are present in the given number x. Now let us define the concept of valid significant figures. The digit alpha n in the number x is said to be valid significant digit. You please look at this. Valid significant digit is some particular digit in the given number. For example, if 5 wants to be the valid significant digit in the given number 2354, what is the condition? We have to see here. If the absolute error in x, absolute error in this entire number x is, that is x minus xa. We know that x minus xa, absolute of that is the absolute error in the number x. This is less than or equal to half of, 1 by 2 means half of 10 to the power m minus bracket n minus 1. So this is the definition we are having over here. It means that the absolute error is less than, this is very important sentence, the absolute error in the value of x is less than or equal to half of the unit of the decimal place in which alpha n appears. We have to look at the place. We have to look at the place of alpha n. We have to look at the place of alpha n. We have to see its unit and we have to take half of that. So if the absolute error is less than or equal to that particular quantity, then we say that alpha n is the valid significant digit. Now let us try to solve one example which is involving the concept of valid significant digit. Now this is the example I have shown over here. Here we have to find the absolute error in the number. This is the given number x. If it is approximated in such a way that it contains 5 valid significant digits, so how many digits are there in this particular number in total? If we see, here are first digit 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 digits present in the given number. Now we want only 5 valid significant digits. So 5 means 1, 2, 3, 4, 5. So we want to stop here. We don't want these quantities, these digits. With these digits we are going to ignore, and we are going to get an approximated value of x, that is going to be 13.151. So 13.151 is the new number which we obtain by retaining only 5 valid digits, and this is the approximated value we are having. And now we are expressing this number 13.151 in the expanded form like this. I have explained you already. That is, this is 1 which is in the tens place, 1 into 10, plus 3 which is in the units place, 3 into this is the slight mistake over here, please correct it. It is 3 into 10 to the power, it should be 10 to the power 0, that is to be taken as 10 to the power 0. 3 into 10 to the power 0, plus this is in 1 tens place, that is 1 divided by 10, that means 1 into 10 to the power of minus 1. This number 5 is 5 into 10 to the power of minus 2, because this is 5 divided by 100, because it is 0.05. That means 5 by 100, therefore it is 5 into 10 to the power of minus 2. As far as this number is, this digit is concerned, how it is? 0.001, that is 1 divided by 1000, that means 1 into 10 to the power of minus 3. So we have expanded this. And now here the unit of decimal place in which the fifth valid digit occurs. Fifth valid digit is 1, and its unit is 10 to the power of minus 3. You please look at its unit. Its unit is 10 to the power of minus 3. It is in the 1000s place. So it is in 10 to the power of minus 3 units place. So therefore, now the absolute error, it must be less than or equal to, as far as our definition is concerned, absolute error must be half into 10 to the power of minus 3. So that is equal to, half means 0.5 into 10 to the power of minus 3. If we simplify this, that is 0.5 divided with 1000. If we do, 3 more digits are going to come in between here, because we are dividing by 1000. So the final value is 0.0005, that is. So this is the absolute error. And now if we this completes the solution of example number 3, that we have computed absolute error in the evaluation of this number if it contains only 5 valid significant digits. Now if we look at this problem, you please have a look at this problem. This is the next example. The absolute error of the number given over here, x is given like 147.1946 is 0.15. The absolute error they have mentioned here, that is given as, absolute error is given as 0.15. We have to find out how many valid digits of x are there if we have this as the valid, that is absolute error in the given number. Try to understand the problem. The question is like this: the number is 147.1946 and the absolute error has been given as, absolute error in this number is given as 0.15. We have to find out if this is the absolute error in this number, then how many valid significants can be there, how many digits of x are valid, and also we have to round off the number x retaining only the valid digits. We have to see what is the answer. So now let us proceed. We know that absolute error must always be less than or equal to half of the unit place of this is the definition we are having, 10 to the power 2, the final how many digits are there, 1 2 1 2 3, so it is half into, if we expand this number, it looks like this: 1 into 100 plus 4 into 10 plus 7 into 1, like this. So the definition states like this: 1 by 2 into 10 to the power 2 minus of bracket n minus 1. So this is the definition we are having. From that definition, the given data, that is absolute error, they have given it as 0.15 less than or equal to, see here n stands for all the digits, number of digits. So here it is 1 by 2, that is 0.5. If we simplify 2 minus of minus, it is 2 plus 1. It is going to be 3 minus 1. So n as it is over here. Now if we simplify this particular thing, then the answer is going to be n equal to 3. So after simplification of this, we are going to get the value n equal to 3, and that means there are only 3 valid significant digits present in the given number x, that is 147.1946, and therefore we can say that when the number x, it is approximated by retaining only 3 valid digits, we can have an absolute error of 0.15. So this is the solution, half of the solution we have completed. Now let us go for the next part. In the next part, we have to round off the given number. We have to round off the given number in such a way that it retains only 3 valid significant digits. How many valid significant digits are there? There are 3 valid significant digits we have seen, and by retaining 3 valid significant digits, we have to round off the given number. If we round off the given number by retaining 3 valid significant digits, it means that we are going to ignore these numbers. In order to ignore these numbers, what we have to see, that means we are stopping at 7 and we have to look at this number, the number next to that. The number next to that is 1, which is less than 5. Therefore, 7 must be kept as it is and the remaining things must be as it is. So the final number, which is after round off, going to be 147. That is the approximated value of x. So like this, we have completed the solution of this example also, and here there was one important concept involved, that was the valid significant digit. I hope you understood very well the concept of valid significant digits. There are so many problems available in the reference book. Please look at the book and try to solve more and more examples. And here are few questions. Please try to answer them and you write your answer in the comment box. This is the first question. This is the second question. This is the third one. This is fourth question. This is the fifth question. So please have a look at this book for further references. So with this, let me stop. Thank you.